number of members in the sets, because you'd be there all day and an infinite number of days. Okay, so the counting method doesn't work, obviously. So you're going to have to use some other device, some other way. Well, he noticed that if you had two finite sets and they had equal size, in other words, they had equal number of elements in them, well, you could come to the conclusion they had the same number of elements by just pairing them off. So you had one element of set A and you pair that off with one element of set B. Then you took the second element of set A and you pair that off with a different element of set B. You took the third element of set A and you paired that off with a third element of B, and so on. And if the two were finite sets and they had the same number of elements, well, then you could pair all of the elements of A with all of the elements of B. So he thought this pairing idea was a good one, and he could apply that, he could generalize that to infinite sets. Okay? So by pairing, you don't have to count. You don't have to count up the number of the elements. You just pair them. Like imagine, go back, I don't know, thousands of years, and imagine you're a smart but utterly ignorant peasant boy, and you're a shepherd, okay? And you've devised this technique. You have no real concept of number. You don't know how to count. You're utterly illiterate. You don't know what an alphabet is. Never seen one. You've never seen any writing, but you're smart. And you devise the following technique to keep track of the number of sheep that you stock in your pen, your sheep pen, at night. Okay? So you have, let's say you have two bowls, and in each bowl you have pebbles. And in the morning, as each sheep leaves the pen, it goes through a little gate, leaves the pen out into the hills, the pasture where all the grass is. Okay, so as each one sheep goes through the gate, you transfer one pebble from one bowl to the second one. The second one initially is empty. Okay, so as each sheep goes through, you're transferring one pebble. So in the second bowl, as the last sheep leaves the pen, you have now a kind of pairing. One pebble, one sheep. Okay, went through the opening, the gate, to the pasture. All right. So let's say he has a red bowl and a blue bowl. So when the sheep return at night for protection, so they won't get eaten by wolves or whatever, every time a sheep comes into the pen through the gate, the shepherd, he transfers one pebble from the second, or blue, let's say, the blue bowl into the red bowl. Okay? So in the morning he transfers the pebbles from red to blue, and in the evening when the sheep come back, he transfers the pebbles from the blue bowl to the red bowl. Right? Now you can see why this technique is useful, because say when the last sheep comes in, you still have one pebble in the blue bowl. Oh, one sheep is missing. Right? Now how does he know that? Well, because in the morning there was a one-to-one, a pairing of a sheep with a pebble. Okay? Now he doesn't know to count. He can't say that there are 33 pebbles and 33 sheep, because he has no conception of number in that sense. All he knows is that there's a pairing between a sheep, and one pebble. Okay, so it's much the same idea that Turing has with infinite sets. He just pairs off the elements of the two infinite sets, and he he specified, like he defines almost. He says two infinite sets are equal in size, and that's size in inverted commas, by definition, if the elements of those two infinite sets can be paired off one to one, like one sheep to one pebble. Okay, so one element of infinite set A gets paired off with an element of set B, and it's 1 to 1. So you don't pair off two elements of A to one element of B. No, it's 1 to 1. So if you pick an element of B, you'll know what the corresponding pair in set A was. Okay, so it's right. So that's the idea. So by using this pairing technique, Cantor is able to define the size of two infinite sets. Right, well, let's do a concrete example. Let's say so we take the set of integers, or even positive integers, right? So 2z. So well, not positive, just the even integers. So in other words, 0 plus minus 1 plus minus 2. Oh, sorry, the even integers. 0 plus minus 2 plus minus 4 plus minus 6 and so on, right? And so that's one infinite set. And then the other infinite set is the set of all binary strings. Set of all binary strings. Okay? Now those two sets, are they equal in size using the definition of Cantor? Remember that definition is two infinite sets are equal in size if they can be paired off, one to one. So can you pair off the even integers with the infinite string? That's the question. If you can, then those two sets, by definition, Cantor's definition, they are equal. Right? Now, is one of them actually larger than the other? Now that would be the case if you cannot pair them off, right? So that's a question we're considering. All right. So I've been talking about this pairing technique. In fact, I've verbally said everything that's here pretty much. So by pairing, you can compare the size without counting. I mean, you can't count an infinite set anyway; it's sort of pointless. Okay? But this idea of pairing is interesting, right? So here's a definition. So 4.12, chapter 4, the 12th thing, whatever, in the chapter. So say you have two sets. Actually, it's quite a long definition. It'll take me well into the third session, so I think I'll stop here, and we'll take this up. It's just the first line, which is the bottom line of this session, but it's the beginning of a long set of definitions concerning sets and definition of functions, different kinds of functions. So I'll take that up next session.